that charge resides at the surface of solid conductors, but that is not uniformly distributed. Perhaps you remember that, unless it happens to be a sphere. And I want to pursue that today. If I had a solid conductor, which say had this shape, then I'm going to convince you today that right here, the surface charge density will be higher than there, because the curvature is stronger than it is here. And the way I want to approach that is as follows. Suppose I have here a solid conductor A, which has radius r of A, and very, very far away, maybe tens of meters away, I have a solid conductor B with radius r of B, and they are connected through a conducting wire. That's essential. If they are connected through a conducting wire, then it's equipotential. They all have the same potential. I'm going to charge them up, and so I get a charge distribution QA here, and I get QB there. The potential of A is about the same that it would be if B were not there, because B is so far away that if I come with some charge from infinity in my pocket, that the work that I have to do to reach A per unit charge is independent of whether B is there or not, because B is far away. Tens of meters, and you can make it a mile if you want to. And so the potential of A is then the charge on A divided by 4 pi epsilon 0, the radius of A. But since this is an equipotential, because it's all conducting, this must be also the potential of the sphere B, and that is the charge on B divided by 4 pi epsilon 0 r of B. And so you see immediately that the Q, the charge on B, divided by the radius of B, is the charge on A divided by the radius on A. And if the radius of B were, for instance, 5 times larger than the radius of A, there would be 5 times more charge on B than there would be on A. But if B has a 5 times larger radius, then its surface area is 25 times larger. And since surface charge density, sigma, is the charge on a sphere divided by the surface area of the sphere, it is now clear that if the radius of B is 5 times larger than A, it's true that the charge on B is 5 times the charge on A, but the surface charge density on B is now only 1/5 of the surface charge density of A, because its area is 25 times larger, and so you have the highest surface charge density at A than you have at B. 5 times higher surface charge density here than there. And I hope that convinces you that if we have a solid conductor like this, even though it's not ideal as we have here with these two spheres far apart, that the surface charge density here will be larger than there.